All right. Okay, great. And 3 separate topics for the price of 1 here. I encourage you to ask questions if you want to deep dive on any of these topics. I will be in London all week at the DroidCon and at the Hackathon on this weekend, so I may be less jet lagged towards the end of the week. If you're at any of those events, please feel free to track me down and ask questions. But we'll get started here with basically, I mean, as you're probably aware, a lot of devices are now octa-core. A lot of the high to mid-end tablets are all quad-core, multi-core devices. And the demand for these high-spec SoCs is just continuing to go up as we move from 3G to LTE, as we have really high-resolution screens, really high-resolution cameras. Demand for processing power in mobile is escalating quickly. Really, there's an upper bound to the improvements you can get out of single-threaded performance. There's a lot of limiting factors in single-threaded performance as well. I mean, there are thermal constraints to consider when you're doing your just voltage scaling or frequency scaling is usually, you know, there's quite a limitation to what you can do with one thread. So even if you can do, you know, you can boost your CPU speed, you really want to focus more on doing multi-core threading when it's an option. The software trend is obviously towards multi-threaded programming. Modern OSs, C, C++11, Java 5, they all have features for concurrency programming and atomic types and threading libraries that you should be taking advantage of. I'm sure you all are. The major software frameworks out there, there are apps that are starting to take advantage of multi-core paradigm. So, you know, you may be familiar with Google switching over to ART in the latest version of Android. It's much more capable of dealing with multi-threaded Java. You know, there's less pauses in the garbage collection now. It's very multi-thread oriented. Also, Chrome Blink, if you're big into Google technology, is heavily threaded now. So there's 3 ways to exploit parallelism as we see them in the ARM world. Obviously, use Neon. There's a single instruction, multiple data architecture in ARM. There's API level parallelizations. You may be familiar with OpenCL, one of the underlying technologies or software APIs in Mali. RenderScript and OpenMP. We've been doing a lot of work in RenderScript intrinsics these days, along with Google, to better support heterogeneous computing on Mali and ARM CPUs. And obviously, you can do multi-threaded programming. If you're familiar with the pthreads library, or you've been using any of the modern revisions of C, C++, there's also even an ARM port of the thread building blocks library from Intel. So that's another option for threading libraries across platforms. So there's several different combinations of big.LITTLE. How many are familiar with big.LITTLE? All right. Great. So, you know, small core, big core environments, they don't necessarily have to be 4 small cores, 4 big cores. When we talk about the little core, though, it's not really in terms, you know, don't really want to think of it in terms of performance or low performing. The benchmarks of the current Cortex A7s offer pretty similar performance to the Cortex A9s from a few years back, and at quite a significant power savings. So we really look at, if you are using processor affinity, affining to the small cores when possible. So I guess the main point of this slide is that, you know, cache coherency is maintained by the or by the CCI. Basically, it's all inside the kernel. If you're working on a Linux or Android system, basically, if you're an app developer, you don't care about this. Just know that it's there, and I'll give you a caveat in another slide as to why you might care. But hopefully you'll never be exposed to that level of the system. This is a quick demo attempting to show the advantages of big.LITTLE. In the first graph, you see basically a quad-core Cortex A15 system was pitted against a 4x4 big.LITTLE system. And in general, obviously the power savings are pretty clear here, with the generally hovering around the 70 percentile for a lot of these kind of real-world tests, running Angry Birds and Temple Run and some other video decodes. In the second graph, you see that obviously if you have 8 cores, you can take advantage of them. The first box there, you gain additional performance just by having more than 4 threads. If you don't have more than 4 threads, then you don't really lose out on performance. The kernel schedule does a pretty good job of managing the threads in the big.LITTLE multi-core system. So things to note when you're doing multi-threading on a big.LITTLE system. Our term, the GTS, the Global Task Scheduler, is implemented inside the completely fair scheduler in Linux. You really shouldn't try to second guess the system in most cases. If you probably, as application developers, don't even want to bother trying to detect what system you're running on, because you may not always be running on a big.LITTLE system. We don't really necessarily expect that of anybody. There is a way to detect if you're running on a big.LITTLE system. I can discuss that with you a little more offline. We get to some coding examples if you want. But basically, we'll trust the system to do the right thing. Pretty much every task will start on a big core, and then as it is necessary, migrate to a little core. For instance, if you're loading a web page, obviously the initial rendering will all run on the big core, and then as somebody's just static or idling, and the page is not moving, then it affines over or moves over to the little core. So you can do affinity, though, if you know that you've got a thread that will be loading objects in the background, loading graphics, doing networking. You can specify that affines to a specific core. It's generally used in gaming for the things that I've mentioned, for a lot of background processes. If you know that your network thread is always going to be running but not going to be taking up a lot of processing power, by all means, affine to a small core. I think we'll have some talks later today that'll show you some of the tools that we have that can show you your system level view and determine whether or not that might be a good idea or not. I guess, so I mentioned earlier, though, about caching, though. If at all possible, you want to avoid sharing data across imbalanced threads. So if you have a very process-intensive task going along and it's sharing data with something that is less intensive, you may start thrashing in your memory coherency or your cache coherency management. So try to avoid imbalanced threads sharing data. If you use a thread management system outside the completely fair thread or the completely fair scheduler, obviously you won't benefit from any of the multi-core or the GTS that we've done, the Global Task Scheduler. So keep that in mind. If you have a thread that you think needs the real-time scheduling system, consider affining to a big core and using the completely fair scheduler. So I think the overall takeaways here are obviously if you're in a Linux-based system, look out for the Global Task Scheduling system. Use basically the stock kernels in your Android and Linux systems, because that's the default in just about everything. And really focus on multi-threaded programming. It is painful, obviously, code maintenance, all the caveats that come along with doing coherency across the system go up, but we expect the trend to continue in the multi-core world. I don't think that should be a big surprise to any of you, but obviously, octa-core systems, a lot more things to take advantage of there. So the next topic that is near and dear to me, because I manage a software library called Project NE10. I'll discuss a little bit more, is Neon. You're probably familiar with SIMD, single instruction multiple data, as it exists in the Intel world with SSE, or in the PowerPC world as Ultivec. ARM also has Neon. So I'm just kind of curious, how many of you have written an app or a library or a game? Anyone? Anyone? Awesome. Okay. And were you ever performance constrained in this system? I think that's kind of a given. Yeah. And were you using Neon in your system overall that you know of? So I think all the hands should have stayed up, because you really were using probably a subsystem that was running on Neon if you're running in mobile. So, I mean, you're probably familiar, as I think most of you are game developers, that the systems are really constrained even more. You have battery limitations, you have CPU limitations. Neon is a great way to move a lot of data or process a lot of data, do fast Fourier transforms and arithmetic operations in parallel. So there's a couple of different flavors now. We have obviously the ARMv8-A. It's probably the version of SIMD you're currently using or have used. It's basically a 16 registers, 128-bit wide. And as we've moved towards AR64, the 64-bit architecture, now there are 32 128-bit wide registers. Neon wasn't originally required in ARMv7 SoCs. I think they really all did include it, save maybe the Tegra 2, which we don't really consider a major factor anymore. It's required in all ARMv8 implementations, and so you can expect it to be there now. And the wide registers can be chopped in whatever size type you want, 8, 16, 32. And now supports, we're moving from ARMv7 supporting single precision floating point to double precision floating point. So it's just, in very simple terms, imagine you're processing an image, an RGB image, and you have, you could go pixel by pixel, row by row, or you could divide your sizes up into 4 different parallel channels in Neon and just push them all through at once. I'll show you some benchmarks further about some of the tests that we ran with fairly simple libraries that you're probably all using. But in general, SIMD is used in just about every soft codec out there. Obviously, a lot of hardware or devices out there have software code decode. But if you need to be future-proof, or future-proof your codecs, Neon's the way to go. It's used in just about every major codec out there. All of the VP 6 through VP9, H.264, H.265. In general, in video codecs, we see probably a 1.5 to 2.5% uplift or time uplift in terms of decode performance. And in DSP algorithms, I know even in Project NE10, we've just revamped our fast Fourier transform. We're getting, for certain size types, a 10x improvement over just regular C code. So pretty significant savings. And then obviously, if you can process your data faster, you can scale the processor frequency back faster. You can get more done. So this is a quick demonstration of, if you took the libav library, this is the codec that underlies VLC or probably most of your home theater systems. We compiled it with Neon disabled, and you see just across the board, I don't know if it's, yeah, okay, it's pretty readable. Most of the decodes got about 100% uplift just by utilizing the basic Neon modifications to the library. I think the only exception in there is the AC3. The encode performance is a bit lower because it spent so much time in the binning algorithm, which doesn't really use Neon, so that's why that one's a little bit low. this is just an example of there's a built into Android 4.4 and KitKat, there's a JPEG decode library. The unoptimized version and the optimized version for Neon runs about twice as fast. And then, so we took this almost 20 megapixel image and ran it through the stock Android decode for JPEG, and then we ran it through libJPEG Turbo, and that got about three times the performance gain. So that's you know, if you're looking for improving performance on a lot of things, Android's great, but there may be newer versions of the libraries out there that you can take advantage of. So that's kind of what the thrust is there. This is a little. So if you want to execute Neon code and you don't have a device or a debugger already hooked up and you just want to see what you can do with a visualizer, this is like a debug environment. The University of Zagat worked with us to make this. It's completely HTML5, so you can go on your web page now and write lines of Neon code. And then you can see in the memory space and the register space what's happening as you step through it, just like you would a source level debugger. And probably early 2015, we'll have the ARMv8 version finished online as well. So it's a simple way to just to see how you can parallelize using the assembly instructions. But I don't encourage you to necessarily go out and write Neon assembly. It's a new architecture for most of you to learn, and that's probably not worth your time at the moment if you don't already know it quite well. But this is a example of all the libraries that either the individual contributors to the library or ARM have been working on. Just about every Android subsystem from RenderScript to Skia has been optimized. You see libav, FFmpeg, liboil, and liborc. If you haven't seen those, are pretty creative runtime compiler for SIMD processing that I think was pretty new to me, and I really enjoyed reading up on that and doing some tests with it. So obviously, use the open source libraries out there. They're available, they're free. You can see across all of Android, just about every aspect, the Blink rendering or browser rendering engine is optimized. All of the soft codecs are optimized, and we're in the process of updating them all to ARMv8 64-bit. You may know that the system or the media core in Android was largely optimized to ARMv7 Neon, and we're working diligently to convert it to what we call C intrinsics, and a little more on that probably in the next slide. So if you want to use Neon in your own applications, obviously your first option is do nothing, because it's already running in a lot of the subsystems. The second step you can take is obviously to upgrade to some of the latest versions of the libraries, especially if you're using open source libraries. It's not really that painful to do. We're working with a lot of the communities out there to do optimizations. So that's a fairly simple step you can take. The third obvious way is using vectorizing compilers. A number of compilers already support auto-vectorization. You're probably using GCC or Clang. Both already do auto-vectorization, but the default optimization setting, I think, in the NDK or the Google NDK is 01. So if you switch that over to 03, you'll help yourself quite a bit with auto-vectorization. You can even help out the compiler a little bit more using the restrict keyword to basically tell it that your type is not going to change and that that's a chunk of data that can be easily optimized into Neon. So if you do go down to write bespoke Neon code, there's a couple of options for you. The C intrinsics and assembly. I generally discourage people from writing assembly these days. You basically can write C-like code, or it is C code. But the key advantage to obviously writing C code that is really intended for SIMD is that it's much more readable, it's easier to maintain, and it's more cross-platform between ARMv7 and ARMv8. And a little fun fact, there is even support for Intel in the ARM_neon.h library. They have about 93% coverage of the ARM intrinsic header file running on Intel, so you're not going to necessarily suffer for using C intrinsics and expecting all devices to be ARM. And then obviously, if you're running JITted code, there are a few little tricks you can do in Java to help the runtime optimize to Neon. But fortunately, ART, we've worked quite a bit with Google and the ART team, and it does a fantastic job of optimizing to Neon in certain cases. So if you don't want to write any C intrinsics, this is, as I mentioned, something near and dear to me. This is one of the first open source projects that we've done at ARM that started out as open source from its inception. It's basically a library of Neon optimizations, but we've also done C implementations of all of them, so you maintain backwards compatibility with devices that don't necessarily have Neon cores. We do unit tests and data tests and make sure that everything's working as expected. We run our output results for every function against MATLAB results just to double check. And it's basically targeted at Android and Linux, but we also test it under iOS every once in a while to make sure it's functioning well. In the Android space, obviously, it's usable across the JNI-JNA boundary. It's modular, so you can take the fast Fourier transform and discard the rest of the code. There are no interdependent or module interdependencies. So it's fairly easy to keep your code from bloating by throwing in a bunch of libraries. You can just pick what you need. It's free. It's BSD, free as in beer, free as in speech. You don't have to contribute any modifications back, but we do encourage you. We do have a path for, it's all up on GitHub, so you can always submit your code back to us if you find that you've had some useful modifications. And we want to make it easy to use, so it's well documented. My email address is on the project any10.org site, along with several of our engineers. And obviously the GitHub issue tracker, we're really responsive, so we want to make sure it's easy to use. Here's a quick example of, we just put a very simple application together that executes through every function and gives you the results, how many iterations it was able to accomplish. So you can see, basically I've got a normalized vector here. The APIs are generally the same across the board, two-dimensional, three-dimensional, four-dimensional normalizing vectors. Then in the example application, you can see the C implementation, the floating point VFP implementation, and the Neon implementation. You can see even getting down into the divide the vector, you can see the C implementation was able to do 11 iterations in the same amount of time that Neon could do 71 iterations. So you can see quite a bit of uptick in some fairly complex math functionality. And we have some physics engine optimizations, we have some image processing optimizations, DSP, arithmetic, across the board. Go check out the header file. You can see just about everything that we've done. It's all up on GitHub. And I encourage you to bug me about that later, ask questions, and check it out. And also, please give us feedback if there's functionality you feel is missing. We're always looking for case studies. We're looking for real-world uses. Let's see. So moving on to the changes in the ARC64. Obviously, I mentioned earlier the register set has doubled from basically 16 128-bit registers to 32. It's no longer a packed register system. This really makes it easier for the compiler to interpret code into assembly level code. So you can see the types, they don't overlap anymore. If you wrote a double or a floating point type, and then you converted it into a quad, you could expect the data to be there in the past. Now that it's remapped. Basically, the opcodes have all changed. There's no longer the V opcodes. The neon instructions are just known by the types as noted in the in the register. I don't know. No, you don't see my cursor. Okay, so the size of the elements is now in the actual data elements in the instruction rather than the opcode. So it's not radically different, but your porting considerations, basically you have to consider this. If you already have assembly code, you have to do a fairly cosmetic edit to your code to move to ARMv8. C intrinsics will port with almost no effort. I hesitate to say absolutely no effort because you can take advantage of the larger register set. If you were coding a really tight loop in intrinsic C, you may be able to widen that loop up a little bit and help the compiler use more registers. But generally, it's fairly simple to recompile intrinsic C code for AArch64. So I don't know, how many are familiar with Linaro? It's a consortium of ARM partners and ecosystems. Great. There are sort of our open source branch, our Linux world of compilers and kernels, and they're doing a lot of work in the core systems in Android as well as Linux to ensure that basically all the libraries that were once written in ARMv7 assembly are done in intrinsics, so they're a little more portable. And something you're probably all very familiar with, it probably doesn't need an introduction, but the native development kit from Google. Neon, so Neon was really supported in the NDK since R5. NDK R10C is out now, but the revision 10 came out in July of 2014. So it supported AArch64. There's two separate packages. Obviously, you can get the 32-bit and the 64-bit version. But it really was driven by you guys. The game developers pushed Google fairly hard to have an expanded tool chain, to have the NDK, and I think the original versions, of Android didn't support OpenGLES, so you could get support by compiling it in the NDK. So really keep pushing the bar forward and letting us know what you need from these tools, because Google's obviously been responsive and sensitive to your needs. And so I'll move on to the last topic here, 64-bit. So a little bit of history first for those. When I keep saying ARMv8, may not be familiar. You say, well, we've got Cortex A8. Is that the same? The original ARM processor was, it came out, it was done by Acorn in 1985. In about 5 years, it was spun into the ARM company, and ARMv4 was popular at the time, around 1998. In the 15 years since ARM went public, we've gone through 4 different architecture iterations, and these included different features for performance and other enhancements. The original cores were some 25,000 transistors, and now we're well into the billions of transistors for some of these larger ARMv8 cores. So just so you're familiar with what the cores and the architecture are, we say ARMv, meaning and then we say v8-A. So it's the extension, it's the revision of the architecture and then what type it is. So an application architecture. That's generally what you're seeing in mobile devices is the ARMv8-A as we move forward into 2015. When we say ARch64, we're basically saying, yeah, this is the 64-bit instruction set. It's a LP64 data model for 64-bit and an ILP for the 32-bit data model. ARch32 covers both the thumb instruction set and the standard 32-bit instruction set, and is all ILP32. So, just basically like Linux and Android all use ILP32 and LP64. But ARMv8-A was one of the most significant architecture changes in ARM's history. It positions ARM to continue servicing current markets and growing into a lot of other markets that we haven't historically been in. In the past, processor architectures really took one of two directions when they moved to support 64 bits. They either created a brand new architecture and excluded any legacy mode, or they added 64-bit to the existing 32-bit architecture, and that really drove complexity of the system and inefficiencies across the board. So because ARMv8-A supports both 32-bit legacy and a new clean 64-bit mode, you can maximize your efficiency across both states. You can continue to execute 32-bit code on a 64-bit system. We've seen really both ARch32 and ARch64 feature new encryption instructions, and we're seeing about a 3 to 10 time uplift in performance across both ARch64 and 32 because of these crypto instructions. Neon is now IEEE compliant floating point, and it does a double. Sorry, you have both, or a wider data set. You have a yeah. So as I mentioned before, you've gone from single precision to double precision and IEEE compliant floating point. The load, acquire, and store release instructions were both a great match for C, C++11, and Java memory models. And not just for a mini-core environment. It improves performance across all thread-safe code, irrespective of how many cores are present. And it removes the need for explicit memory barrier instructions. So in many cases, it can perform, it can really improve performance in any atomic situation, even on uniprocessor systems. The other obvious benefit moving towards 64-bit is the large physical addressing. We had 40-bit LPAE in ARch32, and we're moving to 48-bit in ARch64. This increase to the 48-bit requires that the software creating the page tables is using ARch64. So in theory, if you had a 64-bit OS, even ARch32 applications could take advantage of the larger physical memory. So with the 64-bit addressing enabling larger memories and huge virtual address spaces, I think the 48-bit goes all the way up to 256 terabytes of address space. A lot of commentators have said that the larger address space is you're trying to support more than 4 gigabytes of physical memory, but it's also critical for a lot of modern desktop software APIs. A lot of them come to rely on vast virtual address space for techniques like memory map file I/O and sparse addressing for things like persistent objects. Those desktop APIs are probably migrating to a smartphone near you. The bigger address space also gives you better security. Address space layout randomization, ASLR, depends on having very large virtual address space. Other changes in ARch64, There's now 31 64-bit general purpose registers. This helps increase performance, obviously. It reduces stack use. We went from having 16 32-bit registers to 31. Well, so 31 because there's a special purpose 0 register. In ARMv8, we had, the stack pointer was R13, the link register was R14, the program counter was R15. So in ARMv8, the stack pointer and PC, the SP and the PC are their own separate register now. So and R30 is the link register. So really, you get to you go from 14 to 31 general purpose registers. The function calls are cheaper because you get 8 64-bit registers for passing parameters. Before you had 4. And you go less into the stack and main memory because of this. Really, strictly speaking, the more usable registers reduces the number of stack spills and fills. It permits more aggressive compiler optimizations like loop unrolling and strength reduction and common sub-expression elimination. And as I mentioned before, obviously, AR64, the SIMD registers are now doubled. So your execution state can change on exceptions or returns. Basically, there's 4 execution levels in ARMv8. There's the EL0 being the least privileged, like the user mode. EL1 is the kernel and IRQ space, and all the way down to EL3, which would be your secure monitor. You may have a hypervisor at EL2, but basically you're probably worried about the execution state 0 and 1. If you change between those levels, you can change your execution type. So you could have a 32-bit app running on top of a 64-bit OS quite easily. You could also, you may be familiar with ARMv7, you could switch between thumb and regular modes in much in the same way, but I think the most common thing we've seen, it was really easy to get Android up and running on a 64-bit kernel and still run 32-bit apps. And so basically you can change modes across that boundary. So if you're transitioning to 64 bits, obviously there's quite a few benefits. 64 bits being one of them. But there's the reduced register pressure, the wider registers, both the general purpose and neon. There's less stack spilling, higher precision floating point, really improved crypto instructions, and the larger address space. AR64 was initially supported in GCC 4.8, and then LLVM Clang 3.3. But obviously, there's much better support in GCC 4.9 and Clang 3.5. So what do you do if you've got a 32-bit application? What are your considerations moving to ARMv8? Really, there's no more swap instruction. This SWP and SWPB were used for semaphores that didn't require disabling of interrupts. That's been deprecated in, I think, ARMv6 and v7, but a lot of the processors out there still supported it. It's really gone this time, so don't use that. CP15 was a coprocessor extension for system configuration. AR64 doesn't include support for coprocessors anymore, but we do have what we call the system registers. Load store multiple is now load store pair. There's no instruction predication. There used to be instructions that could conditionally execute. So, if this condition exists, do this in one instruction. Those don't exist anymore, but we have conditional select, which is fairly similar. So you didn't write any of your code in assembly, but you still have to be aware of a few things in C. Obviously, you're probably really familiar with structure padding. If you expected a structure to be a certain size and you've switched over to 64-bit, that size may be padded in ways that you weren't expecting, so don't really depend on a specific size of structure. Obviously, the big no-no, casting between int32 and pointer types. Hopefully none of you are doing that, but look out for that. Obviously, if your pointers have now doubled in size, then your int32 won't handle that. Doing just any sort of bitwise manipulations or magic numbers are also, generally I think you guys are pretty good with writing portable code and you're aware of all of these things, but they still apply switching from ARMv7 to ARMv8. And really, yeah, trust your compiler to do the right thing. We look at multi-arc support in Linux and Android is pretty robust. You can do 32, 64-bit applications and switch back and forth. You can have a 64-bit capable Java application executing or calling JNI 32-bit libraries and vice versa. And then the chart here at the bottom of the slide is basically what you already know. Linux is LP64 data model. And the only real change is the long integer is now doubled, and obviously the pointer size is doubled. So the tool chains I mentioned earlier, ARMv8 to LLVM Clang is upstreamed. We started in 3.3, and that's now stable, as is 3.4. Really, 3.5 is considered the mature version, though. There's the best auto vectorization. There's the best support for anything ARMv8 in that implementation right now, so I encourage you to use that. In GCC, we're stable in 4.8.3. We also have a Linaro trunk 4.8.3 that's a little bit improved over that, and then obviously 4.9, I consider that a mature version. It's just moving into stable 4.9.1, but if you may have noticed in the latest version of the NDK R10C, they switched over to 4.9 as the default compiler, and they're probably going to deprecate 4.6 pretty soon. So if you have the option of moving to a 4.9 compiler for your 64-bit implementations, do it. Great improvements there, and really better stability in 64-bit. In terms of tool chains, I don't expect anybody here, if you're developing an Android app, to switch over to a Linaro compiler for your GCC needs, but Linaro does have their own version that's upstreamed, so if you need a feature that's not quite made it to the mainstream of GCC, it may be in the Linaro version. More importantly, if you don't have access to ARMv8 hardware, you can download a fast model for free. Now, the fast model is pretty limited. There's no frame buffer support, so you can't get graphics, but you could at least test your libraries on a free emulated space for ARMv8. You can also get the fixed virtual platforms there, or basically Linux distribution for those fixed virtual platforms. And if you're looking for tools for the early release ARM Juno boards, these were some early prototype dev boards for ARMv8, then we have all the tools up there for those as well. And most importantly, Lollipop. So the Android Lollipop SDK is out, as is NDK R10C as of, I think, October 20th. You probably know this by now, but Android version 5 has switched to Android runtime instead of Dalvik. ART supports both 32 and 64-bit, and OpenGLES 3.1. The extension pack has a ton of features, tessellation and geometry shaders, ASTC texture compression format. You can go to the website and read the number of features up there, but it's a really impressive improvement. And as I mentioned, 10C ships with both GCC 4.9 and Clang 3.5. It supports 6 ABIs now, the ARM and x86 and MIPS, both in 32 and 64-bit. And as of 10C, yeah, we'll probably see GCC 4.6 deprecated. So some maintenance and marketing slides here, but I also encourage you to do this. The ARM Connected community we launched just over a year ago. I manage the Android Connected community space. It's basically a social media site, but it's for people who are interested in ARM technologies. We have discussions on what compiler flags to use on various Android platforms, porting guides to different devices, a lot of white papers, programming guides, and a lot of discussions there. I encourage you to go there and ask questions, because there are a lot of ARM engineers trolling the site for good questions and eager to get into discussions. There's no, it's all free. There's no maintenance or contracts required. It's just a place to go chat about technologies that you may have questions about. And then obviously ARM does supply technical training. I think we have most of our courses are in Cambridge and San Jose and Shanghai if you're interested. These are all done by ARM engineers, and they're good for organizations or even individuals who thrive in more of a classroom environment. I'm one of those people, you have to nail me to the floor to get me to pay attention to these presentations, so this is a good way to go about doing that. So I'll open up the floor to a few minutes of questions here. Do we have any on any of the three topics?
If anyone has a question, I'll bring the mic in.
Great. So you're all asleep, or this is really, really boring. No, I'll be here the rest of the day.
All right, there's one question here.
Yeah.
So, okay, you mentioned the thermal constraints earlier, and also the, well, basically processing on multicore. So I guess you're saying that if you have a task that could run basically wide, but rather on low frequency or like the low power cores, then it's better to make it wide rather than to run it on a single core that's fast. So basically, if it's more power efficient to spread a task over maybe 4 A7 cores than run it on a single A15 core.
Possibly. It's not necessarily power efficiency that may be constrained. In those cases where you had to have a high performance thread, if you could break it into multiple threads, obviously it's going to vary on the vendor SoCs. We work with we have a huge community with different SoCs, but in general, your cores are physically based on a die, and if you're heating up one corner of that space, one of our partners' SoCs may ramp down it may sense a thermal overload and then scale the frequency down on that core. Whereas if you spread it out over a wider physical space, you have more surface area to dissipate heat from. So it's really is that simple physics of surface area. You're spreading out your processing over a larger surface area. I think in general, you just will benefit from being able to spread that out and then ramp frequencies down, or allow the system really to ramp the frequency down when it deems it appropriate. So that's why I encourage that. Do you have like a specific case where you were seeing an SoC overheat, or you had a single core?
Just,
okay.
Just in general.
Yeah, so just generally threads are good, yay.
Any other question?
All right. I will be here the rest of the day. I'll be in London all week, and over the weekend at the Wearable Hackathon at Google, so some of you might be there, I might see you. I think the presentations will be made available on Molly Developer, but just in case you want to grab mine now, there's the link. Good on time.
Yeah.
And
we'll have
straight to the next one, or 5 minutes?
No, we'll have 5 to 10 minutes until the next one at 10:30.